In exercise number 44, we are asked to find r of t if r prime of t equals ti plus e to the tj plus t e to the tk, and r of 0 equals I plus j plus k. Now, this is actually just basically a vector version of some initial value kind of antiderivative problems that you saw back in Calc 1, perhaps even before you even talked about integrals. Back when you were dealing with antiderivatives, you would have some of these things with position, velocity, maybe acceleration, that kind of thing. And this is a kind of very simple differential equation, actually. But the solution technique is reasonably straightforward. The idea is that we are looking for the position function r of t, and we know that that is going to be one of the antiderivatives of its derivative, r prime of t. Right? Since r prime is a derivative of r, then r is going to be one of the antiderivatives of r prime. So we have the antiderivative, the indefinite integral, of ti plus e to the t j plus te to the t k dt. Always make sure to include your grouping symbols when you have more than one term here. If you don't see why that is needed on the intuitive grounds of having a differential times the function, you'll find out later in this course why that is more important. So if you're not in that habit, make sure you start that habit now. So we could do what I mentioned in the previous video and break this up into a sum of 3 individual integrals. But most of these are relatively straightforward, so let's just kind of take them how they are. Let's see, we can integrate t and get a 1/2 t squared I plus integral of e to the t is e to the t, so we have e to the t j plus, now this t e to the t, this is a relatively simple and common form, so some of you might have it memorized. I actually don't. I don't run into it often enough for that to stick. If you don't have it memorized, there are a couple of ways you can do this. One is you could do parts. This is a very simple parts problem. One step, can come off to the side and work that out. Or this is one where you might recognize that because of the form of it, you expect te to the t to be part of the antiderivative. So, okay, what happens if I take the derivative of te to the t? Well, we get te to the t plus e to the t, and we want to get rid of that one. So if we subtract off an e to the t, which is its own derivative, and you can check that. If you work this out through parts, you get this, or you can just take the derivative of what's in parentheses and confirm that it reduces down to te to the t. It's kind of a little trick for dealing with things that look like this. So we have this, right? But hopefully you recognize that I'm not finished with this line. And I hinted at that when I spoke earlier about r of t being one of the antiderivatives of r prime of t. Because r prime of t has infinitely many antiderivatives. We need to add a constant. But a constant what? A constant vector. Right? We have vector objects we're dealing with here. So there's some constant vector that gets lost in the process of taking the derivative to move from r down to r prime. So we have a description of a family of vectors that r of t could be. We just don't know which specific one. Well, how do we find that out? That's where this initial value comes in. We have r of 0 equals I plus j plus k, right? But we also know that r of 0 has to equal, we have 1/2 0 squared I plus e to the 0 j plus, we have 0 e to the 0 minus e to the 0 k plus some constant, right? So let me clean this up a little bit. We have I plus j plus k is equal to 1j minus 1k plus a constant. We need to know what this constant is. So let us subtract j from both sides and add k. So we have I. Subtracting the j cancels that out. We have a k plus another k, so that looks like I plus 2k. Oops, I missed my hat here. And there's our constant c. So, plugging that back into our expression for r of t, which was this right here, we have 1/2 t squared I, but now we know that c also has an I in it. Actually, you know what, let me, that's fine, it'll take a little bit of time, but I'll go ahead and write this out explicitly. So we have what we found for r of t, which is all of this junk. Oh, there we go. Plus this vector we found for c, that was I plus 2k, right? And we want to write this in as simple a form as possible, so we want to collect the i's together. That means we have 1/2 t squared plus 1 I, plus, there are no other j's, there's only this first one, so we have e to the t j, plus, and collecting the k's together, we have t e to the t minus e to the t plus 2 k. And there we go. That is the particular antiderivative that we're looking for, the original function r of t. Again, r prime of t will have infinitely many antiderivatives. We want the specific one that satisfies this condition, where r of 0 equals I plus j plus k. So you have that. Now this is all using the I, j, and k notation. Again, you're always free to switch that to the component form with angle brackets. You could certainly have started this by saying, okay, so r of t is the integral of r prime of t, which is t e to the t t e to the t dt, right? So then you get your 1/2 t squared e to the t e to the t minus e to the t plus a constant, right? Same work, it's just some people find this slightly easier to read and write, putting it in angle brackets with commas rather than having the i's and j's and k's. And you would still continue to say, okay, so r of 0 equals, and I put in the ijk first. I would normally put that last, but it doesn't matter. I can go ahead and say that this is the one we're given is the 1, 1, 1, and that needs to equal the 0, 1, -1 plus c. So then when you subtract these vectors, right, you have a vector on the left and a vector on the right. So when you subtract this, you have 1 minus 0 is 1, 1 minus 1 is 0, and 1 minus -1 is 2. And now you've found your value of the vector c, and then you just have to plug that in. So r of t equals, and I'm running out of space, but you get the idea. You just stick all of these into their, actually I might be able to fit it. We'll see what happens. Because we have this vector plus c, so we have the 1/2 t squared plus 1, e to the t plus 0, and t e to the t minus e to the t plus 2. Had to kind of cheat a little bit there, but there we go. So, whichever way you want to solve these things here, whether with the ijk or with the angle brackets, whichever is easiest and most convenient for you. I'd recommend, at least at the beginning, to practice using whichever method a particular problem is stated in. Most of these problems use i's, j's, and k's. Some of them have angle brackets. Try at least at first, using both of them so that you know that you become comfortable with both and you can use them both. And then once you know that one of them, once you know that you can do them both if you have to, then whichever one you like best, you can probably do most things in that. Or you might just stick with what I will often do in this class, which is to generally stick with whichever form of vectors they present in the problem so that we're not switching too much. But kind of depends on the circumstances.